Hi everyone, welcome to Astronomy 236. This is week 5 now, and this week we're going to be talking about more cosmology, which is the study of the entire universe. In this lecture bite, we'll be talking about the chronology of the Big Bang. So basically, from the start, how it all went down, what all happened in the history of our universe. So this is a big lecture. So last week, we talked about the Big Bang theory, and we have observational evidence for the idea that galaxies and everything in the universe are expanding outwards. And the further away something is, the faster it appears to be receding away from us. This is Hubble's law. We also have a mathematical theory, the Friedmann equations, which come from general relativity, that we can use to describe the scenario of a universe going through the Big Bang. So now that we have these two pieces of observational and theoretical evidence, we can put them together to figure out what the math tells us actually happened and learn a little bit about what the history of our universe might be. Now, throughout this lecture, a lot of what we're going to be talking about is purely theoretical. Some of the stuff we're going to be talking about, we can't even possibly hope to observe because there's no light left over from that time in the universe. But if we trust our laws of physics, and to a certain extent we should, not all the way, which I'll explain later, then we should be able to get some idea as to what must have happened in this scenario based on just the math. So first, I'm going to review a few concepts which are going to be important. And I'm going to start off with scientific notation. Now, I've used scientific notation a little bit here throughout the course, but I haven't really gone through and described it. But it's a very important part of today just because we're talking about such huge numbers and such tiny numbers. So I want to really make sure you all understand what I mean when I use scientific notation. So here I'm writing scientific notation 10 to the power of 0. And basically the idea of scientific notation is it's a way of compactly writing very large or very small numbers by not just writing out all of the digits, but by essentially telling us how many digits there are. So if you want to read off what scientific notation means, one way you can think about it is that if you have 10 raised to some power, to some exponent, that tells you how many zeros there are after the 1 in that number. So in this example, 10 to the 0 is 1. There's a 1 and there's nothing else. If instead we look at 10 to the 3, there's a 1 and there's 3 zeros. So 10 to the 3 is 1,000. And we can just keep on going up. So the other thing I want to do is kind of give you a refresher. You all know this, of course, but these numbers are really big. And I just want to give you a visceral understanding for how large the numbers are that we're talking about. So here's 10 to the 3 dots, 1,000 dots. And this is a lot of dots, but it's a manageable number of dots. There aren't so many dots that I couldn't, count them or do something to all of them. But the deceptive thing about scientific notation is how quickly these numbers get bigger. The difference between 10 to the 1 and 10 to the 3 is much smaller than the difference between 10 to the 3 and 10 to the 6. So here's 10 to the 6. 10 to the 6 is 1 followed by 6 zeros, and that's 1,000,000. If I do this viscerally and I show you the number of dots, it's a huge amount. So it's hard to tell right now, but I'm scrolling through this image with 1,000,000 dots. And occasionally over on the left, you can see some numbers slide past. So that's 300,000 right there. So we're only a third of the way through scrolling through this image. And you can see I'm scrolling pretty fast. I'm not taking my time or anything. And here's halfway through. So that's a lot of dots. If you want to really understand what 1,000,000 is, it kind of helps to see 1,000,000 of something. And you can understand how much more massive this is, a number, than 1,000, even though 10 to the 3 and 10 to the 6 may not sound that different. And as you go even higher, it gets more and more absurd. It gets more and more overwhelming, the numbers that we talk about. So if I go up from 10 to the 6 to 10 to the 9, which is 1,000,000,000, I would have to scroll through that image of all of those 1,000,000 dots 1,000 times. So imagine just how long it would take to even look at all of those dots. And of course, not to mention do anything carefully. So numbers get really big really fast when you use scientific notation. The other thing about scientific notation that I want to review is what happens when you try to go small. So here I'm showing 10 to the minus 3. And what I mean by this is 1 over 1,000. So it's exactly like 10 to the 3, except now I'm dividing, which is that minus sign. So 10 to the 3, you can think about it as 1 in 1,000, or 0.001 here. So viscerally, 1 in 1,000 means that one red dot in the corner out of all of those black dots. And similarly to positive exponents, the faster you go, the lower you go in negative numbers in your exponents, the smaller and smaller this fraction is. So 10 to the minus 6 is literally 1 in a million. And I'm not going to make you watch this entire video again, but imagine trying to find the one red dot in this video. I looked through several times myself and I couldn't find it. So I trust that there is one. The website says that there is one, but I don't know. So when you think about what the chances are of finding 1 in a million, think about choosing any one of these dots at random, maybe closing your eyes, scrolling on your screen and putting your finger right on that dot, and that being the one red dot in all of these. So 1 in a million is really tiny, and 1/1,000,000th of something is a very small fraction. Okay, now that we've gone through scientific notation, a couple of other basic physics things that are going to be really important. So the first thing is when gas is compressed, it gets hot. I showed this GIF last week, and we recall that this fellow is pushing this plunger in. He's compressing the gas in that tube, and he's making it hot enough that it actually reaches the point at which cotton, which is inside the tube, will ignite spontaneously. It'll start to combust and turn into and start burning. So just by compressing a gas, you can make its temperature very hot, which of course is important because in the Big Bang, we're talking about stuff that's all very, very dense, very, very close together at the beginning, and then it expands outwards. And finally, just keep in mind that when I say that something is hot, what I'm really talking about is that the particles in this material are moving around fast. So you remember from a couple of weeks ago, we talked about how temperature is related to the speed of things moving. So the hotter something is, the more stuff is moving around, the more often it'll collide, the harder those collisions will be. And that causes this food coloring to disperse faster in this hot liquid over on the right than it does in the cold liquid on the left, because the water molecules are really moving around and bouncing around really quickly and causing everything to get spread out, whereas in the cold water, it's really not happening much, and it's all just settling to the bottom, and it'll take much longer for the food coloring to evenly disperse throughout the cold water. All right, so all of this said, we're going to start talking about the evolution of the universe. And the one most important thing about the universe that defines what happens at every given stage is its temperature. The universe went bang, so it started off very small, very dense. When I say small, I don't necessarily mean that the universe was all compressed into one point. I just mean that the amount of a given material is compressed into a small point. There may be infinite amount of given material outside of that region, but everything's very dense. It's very closely packed together. And then when it goes bang, it starts expanding. And because it expands, we know from our study of how gases respond to being compressed that if it starts off hot and compressed and it expands, it will cool down. So the cooling of the universe is what causes all of the phenomena that we're going to talk about today and what allows all of this phenomena to happen. So I'm going to start from the very beginning. And it's hard to do that because for the first 0 to 10 to the minus 43 seconds, we really can't see much of anything. Now, here's my first scientific notation use here. 10 to the minus 43 is an unbelievably small number. 10 to the minus 6 is a millionth, so 1/1,000,000th of a second. 10 to the minus 9 is a billion, 1/1,000,000,000th of a second. you have to go millions and millions and millions, 6 times, not 6 million, but 6 million of a million of a million of a million of a million to get close to 10 to the minus 43. So this is an incomprehensibly small fraction of a second that we're talking about. And during this time, the universe is so hot and so densely packed together that we just can't describe it with our existing laws of physics. It's massive. There's a lot of mass in a small area. So we need to understand how gravity depends and how gravity works in these circumstances. But it's also so closely packed together and on such small scales that we need quantum mechanics to help us. And unfortunately, physicists do not have a way to describe gravity with quantum mechanics. There is no theory of quantum gravity that works to describe our universe yet. Now, this is one of the top priorities for theoretical physics in our century, and it has been for a long time, ever since the last part of Einstein's life even. But we've never been able to crack it. Until we do, this first 10 to the minus 43 seconds of the universe will basically remain a mystery. We have no way of describing them with our laws of physics. We have no way of observing them because all of the light from here is essentially lost and scattered by stuff that happened later. So for now, this will have to remain a mystery. We have a little bit better idea what happens for the next fraction of a second. So over the course of 10 to the minus 43 seconds to the first 10 to the minus 6 seconds, so from this incomprehensibly small fraction of a second to the first millionth of a second, the first microsecond, we have some idea. Throughout this entire time, the universe is cooling down. It's mostly made up of elementary particles, so like the very most basic building blocks of matter, even more basic than neutrons and protons, because it turns out the neutrons and protons are made up of smaller particles themselves called quarks. So there's these really tiny elementary particles like quarks and other stuff whizzing around. And there's lots and lots of light, lots of photons whizzing around. Everything's at extraordinarily high temperatures. And in fact, everything is at such a high temperature that the laws of physics are pretty different at this stage of the universe as they are in our everyday experience. So we talk about during this stage of the universe, essentially the laws of physics, the forces that govern everything that we know about, coming to be the way they are after they started off different because everything was so hot. And throughout this time, essentially energy and matter are basically interchangeable. There's so much energy and matter whizzing around and colliding with itself that mass is turning into energy and vice versa via E equals mc squared just on the reg. And it's just totally chaotic. All of this stuff slamming together in very small, tight areas, incomprehensible. We just don't have a way to understand it with our minds. Yeah, so as I said, frequently there are collisions between light and matter. So light is getting bounced around. It can't travel far. So if I were to try to shine a flashlight through this very, very dense soup of material, it would not go far. It would just be totally opaque. And one of the strange things that's important that's happening during this time is something called the inflationary period. This is less well understood than other parts of the Big Bang Theory. We think as physicists and as astronomers that there's probably at least some truth to the theory of inflation, but we don't have any observational proof yet. We have problems that it solves, but we don't have a prediction that it's produced that we can then go out and test yet. Of course, people like the Bicep 2 team are working really hard to do that, but so far they haven't been successful, as we learned about in the very first week of this course. So during the inflationary period, the idea is that the universe underwent an even more rapid spree of expansion, extremely fast, much faster than anything that happened before or anything that happened since. And this graph is showing how that works. So on the y-axis, it's showing how big a certain part of the universe was at every given time. And on the x-axis, it's showing the time. And over this extremely small amount of time, from 10 to the minus 36 to 10 to the minus 32 seconds, you can see that the size of the universe jumps by many factors, from 10 to the minus 45 or so to about 1 meter. So extremely fast expansion. And this solves problems like explaining why the universe seems to be so similar all across the sky, no matter where we look. Even though if this inflationary period hadn't happened, in principle, we should have been able to see differences just based on the different initial conditions, the differences between one part over here in the universe, one part over here, and one part over here. So inflation seems like it makes sense, but we don't really understand all of it very well, and we haven't really tested it. So this part is a little bit more tenuous than the rest of the theory. All right, so let's zoom ahead to the second microsecond or so of the universe's existence. And this is where stuff starts becoming a little bit more normal to us. And this is where our theories start to hold together a little bit better. And from here on out, everything gets a little bit more and more certain as we get more into the realm of physics that we can test with our theories, and we get more into the realm of things that we can actually observe in our own universe. So over the second microsecond of the universe's existence, and all the way out to the first second or so, we're starting to get the first composite subatomic particles. So what I mean by that is particles like protons and neutrons that are actually made up of smaller particles like quarks. The universe has now cooled off has cooled off enough that quarks can stay together. They're not moving around so rapidly that they would just immediately crash into another couple of quarks and then leave again. They crash into them and then they get stuck in these protons and neutrons. And they are now essentially bound there. So instead of having this soup of quarks, we now have soups of protons and neutrons. So matter is starting to feel a little bit more familiar to us. So once we have protons and neutrons that are forming and staying put, we can start to see that they start binding themselves together. And in the first few seconds of the universe's existence, through the first few minutes or so, we start to see the first nuclei form. And when I say nuclei, I mean two particles, like a proton and a neutron, that would normally form together in the nucleus getting stuck together. Because of course, a proton is a hydrogen nucleus, but for our purposes, we want to talk about the heavier stuff in terms of when this first starts to happen. So if you have a proton and a neutron, that forms a nucleus for something called deuterium, or 2 hydrogen. It's a heavy flavor of hydrogen. It has more mass in its nucleus. It's twice as massive as a normal hydrogen because it has both a proton and a neutron in the nucleus. So deuterium forms right around now. And in the Big Bang, we have the opportunity for the deuterium to form, and then those deuterium can crash into each other and they can make even larger nuclei. So here's an example of how this might go. If you have 2 proton-neutron pairs that collide together to form deuterium, then those 2 deuterium pairs can form together and create a helium nucleus. So you can start building up heavier and heavier nuclei during this time period, during these first few minutes of the universe. So here's a graph showing how all of this happens. So it's a little bit of a complicated graph, but I'll try to go through and explain it carefully. So on the y-axis, it's showing how much of each material there is and how much of the universe it comprises. And this is shown in log units. So essentially, these numbers over here on the y-axis are the exponents for scientific notation. So if something is over at 0, or a little bit below 0, then that means that the fraction of the universe that that element makes up is a little bit less than 1, so a little bit less than the entire universe. So for hydrogen, which kind of hovers always near 0, you can see that hydrogen pretty much always makes up the entire universe throughout this time period. Only very small fractions of other elements come to exist. And conversely, down here at the very bottom, you can see this red curve that slides in at about 1 second, it is about at -12. And that's the curve for deuterium. So at a time of about 1 second after the Big Bang, our theories predict that deuterium should make up only about 1 out of 10 to the 12 parts of the universe. So out of 10 to the 12 atoms in the universe, almost all of them should be hydrogen, and only one will be deuterium. But over time, you can see that this rises quite a bit. And this is happening as these first nuclei are forming, and there's more time for the nuclei to bound together. And crucially, the collisions are getting less and less violent over this time, so that when two nuclei do collide, they don't just totally split apart again. Or when something like that happens, they just don't just get lost. The energy, the heat, the temperature of the universe is decreasing enough that we can start getting these larger and larger things to stick together without totally immediately going apart. So as time goes on, you can see that the curves for these other elements rise. Deuterium peaks at about a minute or 2 minutes after the Big Bang. Helium keeps rising. And the reason deuterium peaks and goes down and helium keeps rising is because deuterium eventually gets made into the helium. And this causes the total amount of helium to go up, but the total amount of deuterium to fall down again. And then you can see that there are other elements that are going along like this as well. So you even get the creation of a little bit of lithium and a little bit of beryllium, but the levels of these are very low. So we're talking about 1 in 100 million or so atom, or 1 in a billion atoms of lithium for every atom of hydrogen. So the process by which this happened is called Big Bang nucleosynthesis. And I wanted to show you this paper because it includes our good friend George Gamow, whose book we read a couple of weeks ago, and who's wrote this very nice book about how the sun is powered. He actually wrote this book before he wrote this paper. So the book that he wrote is not out of date because we understand a little bit more about how the elements in the sun came to be. It's a famous paper as well, not only because it ended up being very accurate, and it was the first paper to point out that this could be how the hydrogen and helium in our universe formed, but also because it has a pun in its author list. So the story goes that the first author, Ralph Alpher, was a student of George Gamow, and they wrote this paper together. So the paper was originally going to be authored by Alpher and Gamow, but George Gamow was a bit of a jokester, and he decided that he should include a third author, Hans Bethe, in the middle, because if he did that, then the paper's authors would read Alpha, Beta, Gamma, which sounds a lot like Alpha, Beta, Gamma, the first 3 letters of the Greek alphabet. So this ended up making the paper a very memorable one, and is probably one of the most famous papers in all of astronomy because of that pun. So if we look at what the periodic table looks like right after the Big Bang, we've actually managed to form much of the universe's material. Most of the mass of the universe today was formed in the Big Bang. All of the hydrogen that we see today around us was formed right in the Big Bang in this first few minutes. All of the helium, a little bit of the helium was formed later, as we'll get to, but most of it was formed right after the Big Bang. And even some of the lithium in our universe was formed in the Big Bang. But all of the heavier elements after that were not really formed much at all. We saw a little bit of beryllium popping up on that graph, but it was such a negligible amount that it doesn't really compare to other sources of formation. And we'll learn more about that later on. But this is kind of the point of this course. Where do the elements that make up everything we see come from? So now you know that if you look at your phone and you know that it has a lithium ion battery, that probably some of that lithium in your phone came straight from the Big Bang. So why did the Big Bang nucleosynthesis stop? We formed hydrogen. It then crashed into each other and fused into helium and deuterium. Why did Big Bang nucleosynthesis stop there? Why didn't it keep forming more beryllium and lithium and even heavier elements? And the answer is there was only a very small range of temperatures where Big Bang nucleosynthesis could actually happen, because the universe has to be hot enough for these collisions to not totally break up all of the nuclei that have been formed. If you get a nucleus stuck together, it has to stay stuck together in order for it to build up meaningful amounts of these materials. But the universe also has to be hot enough to keep crashing these elements together and making heavier and heavier elements. And unfortunately for the creation of other elements in the Big Bang, it was only this perfect temperature for a couple of minutes right after the beginning of the universe. So after the first few minutes of the universe, it had cooled down enough that fusion of these elements, the fusion of helium into heavier elements, just wasn't efficient. And these elements were never continued to make. All of these abundances, the ratios of the elements just froze out and were essentially constant after those first few minutes until much later on in the course of the universe, which we'll get to later on in our course. So Big Bang nucleosynthesis happened in the first few minutes, and then it shut off, and that was the end. And that's where all of the hydrogen, helium, and deuterium in our universe comes from, and much of the lithium as well. All right, so that was an eventful first few minutes. After that, things calmed down a little bit, and the universe kept cooling and kept cooling. But the next really important event that happened was not for another 300,000 years or so. And this is when we start to get the formation of the first atoms. Now, we were just talking about the formation of the first nuclei, but these nuclei were totally ionized. The temperatures were just so hot that the electrons could no way stick to the nuclei. And it would take many, many years, hundreds of thousands of years, for conditions to cool down enough that these atoms could hold on to their electrons and the universe would stop being ionized. And this is a particularly important time in the universe's history, at least from our perspective, because this is the first time that light can start to travel freely. As soon as the electrons that are bouncing around in the universe are attached to atoms, the universe becomes transparent. Electrons tend to screen light. They're pretty opaque. But as soon as those electrons get attached to protons and neutrons, then it takes a very precisely colored color of light to be emitted or absorbed by that electron. And those are the wavelengths that correspond to the quantum energy transitions. So you'll have still an opaque universe in some particular wavelengths of light. But for most light, it doesn't happen to fall at one of those perfect transitions, one of those perfect colors. It's one of the fingerprints of the elements. Light can start to travel freely. And the light that started to travel freely 370,000 years after the Big Bang, over 13 billion years ago, was observed by us. And this was actually the glow from the Big Bang that was observed by Penzias and Wilson when they detected the cosmic microwave background radiation with their antenna in New Jersey. So I wanted to give you a little bit more information about the cosmic microwave background. We know from observations that it's very close to a black body curve. And right now, it's a black body curve for a very cold object because it's been stretched out. The wavelengths of light have been stretched out over the eons from the very short, hot wavelengths, high energy wavelengths that it was emitted at back in the early universe to the very cool, stretched out wavelengths that we see it at now today in the microwave region of the light spectrum. And we've built instruments and flown satellites to make very careful maps of the cosmic microwave background. And here's a map. So this oval shows the entire sky stretched out, kind of like a map projection. You might see an atlas of the entire world. And the color that we're showing is the temperature, where a temperature of 0 degrees Kelvin, so absolute zero, very, very cold, is black. And a temperature of 4 Kelvin, so still very cold, is red. And what you'll see is that this map is almost perfectly uniform. It's entirely this green color. So what that tells us is that the temperature of the cosmic microwave background, the temperature of the universe that we observe was very, very constant. This is one of the reasons why the theory of inflation is appealing, because it kind of explains why the universe was so smooth and so homogeneous any way we look, even though in principle it would have been hard to achieve that had there not been this rapid inflation, this rapid expansion of the universe very early on. So this map is startling. It's so perfectly clean. It tells us something very fundamental about the universe, which is that everything, everywhere we look around us, is very similar, and that there really isn't a special part of the universe. But there's more that the cosmic microwave background can tell us. So what I'm going to do is I'm going to zoom in on this color scale, and I'm going to replot it. So now look over here on the right. This color scale is much smaller. We've zoomed into a region of just a few percent, less, I think 1% of a degree Kelvin, or of a degree Celsius. And now in this new color scale, we can start to see some features. So what's going on here? There's this kind of yin-yang pattern, and there's a region that's red that appears to be hotter, that appears to have a shorter characteristic wavelength of light that we're receiving on one side of the sky, and on the other side of the sky, there's a region that seems to be cooler, that has a longer wavelength characteristic color of light that we see. So this is actually due to the Earth's motion, and this is a Doppler shift. So somewhat confusingly, the red region here is corresponding to blue shifted light that we're moving towards. So we see those wavelengths a little bit stretched closer together, and therefore we see it as a little bit of a hotter black body. And that blue region over on the left in the bottom is where we're moving away from. So Earth is actually moving with respect to the rest frame of the universe. So there is some velocity that we have with respect to the entire universe, and this is how we can measure it. So this is also very illuminating. It tells us something kind of fundamental about this radiation. But there's more physics to be found if you dig a little bit deeper. So if we subtract off how we think that our velocity should be with respect to the motion of the universe, or with respect to the rest frame of the universe, we can start to see even more patterns. And this is where stuff gets really interesting. So the first thing you may notice is this big red band across the center. This is actually interference from our own galaxy. Dust in the plane of our galaxy is a little bit hotter than the typical radiation coming from the cosmic background, coming from the early universe. So we just should ignore that red region. Take a look at the scale over here on the right again. I've zoomed in much, much more, even more. These are truly tiny changes in the temperature of the universe over different parts of the sky. But these black and blue regions over on the right, and these kind of warmer red or yellow and green regions over on the left, those are real. These are real differences in the temperature of the universe, and in particular in the density of the gas that emitted that light 370,000 years after the Big Bang, over 13 billion years ago. So here's what our latest and greatest observations look like. Those previous observations were from a NASA satellite from the 1990s called COBE, the Cosmic Background Explorer, COBE. The new data is from the European Space Agency's Planck satellite. And the resolution, the sharpness of this image is stunning. You can see these gorgeous little pockets of warm gas that emitted this radiation that we saw from very, very far back in the early universe. So this time, 370,000 years after the Big Bang, was really important to us and to our knowledge of the universe. After that time, it was a little bit harder for us to see. These are called the cosmic dark ages because we no longer see the glow from the after effects of the Big Bang. That was emitted earlier, and we just see that light continuing to come to us. We no longer see that glow, and we don't see any other light as well, because this is before the gas that now makes up the universe. The universe is now mostly made up of hydrogen and helium gas, has coalesced into larger things that produce their own light, like stars. So we call this the cosmic dark ages. But we have some pretty good guesses as to what's going on, and this is an absolutely crucial part of our universe's formation. And what I'm going to show you here are some computer simulations of what we think must be going on, based on what we think our initial conditions were, what the universe looked like at this point when the cosmic microwave background was emitted, and based on what our final conditions are, what we see around us in the universe, what galaxies and galaxy clusters look like. So I'm going to show you some fun simulations. But to give you a perspective as to where these simulations are starting from, I want to show you this map of the cosmic microwave background again from the Planck satellite. And in particular, I want to zoom in on some particular hotspot, some particular bright point in this diagram. Let's choose this one just for fun. And what I want to do with this is I want to figure out and imagine what could be causing this particular bright spot. In this region of the universe, the gas was a little bit hotter than everywhere else. And one of the reasons why this might be is because that gas might be compressed a little bit more than everywhere else. Just randomly, that gas might be a little bit squeezed tighter together and therefore a little bit warmer. So what does this mean going forward in time? So this is a computer simulation, and I want you to imagine that this yellowish bright blob over on the right-hand side is one of these small regions, these small hot regions from the Planck image. And now we're going to fast forward in time to see what happens if there's a little bit more dense gas in one part of the universe than the other, and see what happens as we go forward and as we let gravity start to take over and do its thing. So what you'll see is that pretty quickly, gravity starts to pull all of these denser regions together. You can see these filaments forming as little stretched parts of gas come together into these little tubes, and then these tubes collapse down into these little balls, these little clusters. So what essentially happens is from this fairly uniform universe filled with gas with these tiny perturbations in the density, these tiny little dips and wiggles in the temperature of the gas, we start to form the largest structures in our universe, clusters of galaxies and galaxies themselves. Each of those little dots was a galaxy or a cluster of galaxies. So this is a similar simulation. And this is kind of the latest and greatest simulation that scientists have today. It's the state of the art. It's called the illustrious TNG simulation, where TNG means the next generation of illustrious simulations. And you can see these beautiful streamlines forming. We call this the cosmic web. The bright colors here are gas and how much gas there is at every location. And you can see that along the cosmic web, you have higher densities of gas, and you have higher densities, in particular, in small, bright regions. And each of those little bright dots, those little tiny dots, is one galaxy. So we can zoom in even farther to see how this collapsing gas can produce galaxies like the ones that we observe in our universe. So I'm going to start this simulation. This is a little bit more of a complicated visualization than the others, but I'll explain what all of the parts are. So this the large screen, the main screen, is showing the distribution of gas. And there's another view of that in the bottom right corner here. Over in the left corner is a zoom out of the larger region. You can see that kind of stuff is closing in and coming in close from far away. So it's a zoom out view. And then this second panel here on the bottom right, the middle panel, I suppose, is showing light from stars. So eventually stars are forming in these galaxies after the galaxy collapses down. And the simulation will go on for a few minutes, but I'll let it play to completion because it's absolutely gorgeous. And it shows how out of the kind of random, chaotic nature of the cosmic microwave background, we can form these beautiful structures like spiral galaxies as a result of all of this gas collapsing down together. So right now, they're showing a couple of different views of different materials. So for example, this is how many heavy elements, heavier than hydrogen and helium, are in the gas everywhere you look. This is how fast the gas is moving. They're kind of spinning around at one point in time, but they'll start evolving forward in time shortly again. This is how bright the objects of the galaxy would look, and the particular color red emitted by hydrogen gas. Okay, now we're back to gas density. And you can start to see that there are little other galaxies that come by and whiz by and interact with the galaxy. And this process is causing the galaxy to develop these spiral arms, these density waves. So it's essentially like waves in a pond caused by these perturbations from stuff outside of the galaxy flying through and essentially causing ripples in the galaxy, ripples in the stars. And you can just see that this process continues. There really is no time in this process when a galaxy is finished, when a galaxy is formed. Galaxies continuously evolve all throughout cosmic time. And if you play these movies forward, you can kind of see how you get the extreme diversity of galaxies that we see in our night sky. So inside of those galaxies, a very similar process is happening. So this is a simulation of a much smaller region of gas within a galaxy with very similar perturbations, very similar random fluctuations. But these fluctuations are so small that instead of forming galaxies and clusters of galaxies, they form individual stars. So if I play this forward, you can see very similar stuff happening. You get those filaments forming. You can see that the gas is now dispersing away in some parts as well. And in a second, we'll zoom in and we'll start to see some regions becoming very, very dense and starting to form stars. So stars will appear to pop out. There's the first one over here. It's this white dot that's shooting kind of through the middle of the screen. And now, as the gas is getting more and more dense and coming closer and closer together, stars are just being formed to left and right. You get these little knots of gas that just keep collapsing and keep collapsing. And eventually, get so close together and so hot that nuclear fusion can turn on and they can produce their own light. And you get these stars just shooting out. And this is how gas from the Big Bang eventually works its way and creates the structures and creates the order that we see in our own universe. And we'll talk more about star formation shortly in our course. Okay, so that was a very brief history of the universe. And I'm going to come back to this slide that I showed at the very beginning of it, where we talked about how the temperature of the universe really rules what happens at all times. And we can see that as the temperature cools off, larger and larger things are allowed to form. So very early on, we had only elementary particles, quarks, and photons, light, bouncing around and colliding with each other often. But as the universe cooled down, things got to the point where we could start to form protons and neutrons. And eventually we could form atoms and put those neutrons and protons together into nuclei. And then a much later time after that, we can start to form larger structures as gravity takes over on the gas that's been formed and creates all of the order that we see today.